So welcome to this class. Briefly, in the last class we discussed about the importance of calibration and how to evaluate the image compression factor, field factors, and how to calibrate. We have discussed with several methods. In this class, usually we will go through the common artifacts. Common artifacts and which are induced during reconstruction. Okay. So the first common artifact is usually present is we called it as a trajectory aberrations. Trajectory aberrations. And the local magnification effects. Okay, so it means that because of these two trajectory aberrations and the local magnification effects, so there will be a discrepancy between the reconstructed data and the original structure of the needle specimen, Okay, so this is induced by two factors. One is the imperfections in the reconstruction procedure, and the another factor is the experimental effects during experiment. Okay, these experimental effects are due to the induction of deflections in the flight of ions. Okay, so in these experimental effects, the most common observed is the roll-up effect. And Wolf et al. Has described that these artifacts due to the roll-up effect are usually observed near the edge of any terrace in FDM. Okay, so if you have a needle specimen which is having a series of atoms, okay, and these are the terraces: first terrace, second terrace, third terrace, fourth terrace, and usually the roll up happens at the edge of these terraces. What does it mean? It means that the movement of an atom on the surface prior to its field evaporation and departure. Okay, so if you zoom out, it might possible that the atom which is present in this location, it can roll out. So this is called roll out. Okay, and the atom will roll along the edge of terrace, and it is just above the position of that particular atom. Okay, so this is called roll up effect, and it is usually seen at the edge of the terraces. Now another kind of, we call it as because due to the effect of experimental effects, this is called trajectory aberrations. Okay, and these aberrations usually are intrinsically related to the distribution of electric field in the vicinity of the needle specimen or the tip specimen. Okay, so this is intrinsically related to the distribution of electric field. Okay, this what happens is that it induces the undesirable lateral displacements of ions during any instant of their flight. Okay, so this trajectory aberration is mostly internally connected to the or related to the electric field distribution around the needle specimen, and it induces a lateral displacement of the atoms or the ions during instant of the flight. Okay, and this directly is affected by the localized, it means that they directly affected by the localized variation in the electric field. Okay, and this results in so this usually happens near to the zones of high, it usually results to the zones of high and low density of ions that hits to the detectors. Okay, so it means that the low or high atomic densities on the detector, so if you have a detector, you may get these zones of high and low regions as zone lines or poles. Okay, so these are all low atomic density regions. Okay, so this is related to your distribution of electric field in the vicinity of the needle specimen. Usually these are located at poles or zone lines. Okay, these are the examples where you can see that there is a depleted zones. These are called depleted zones in any FDM image. Okay, this is due to the electric field in the vicinity of these zones. Are discontinuous. Okay, this discontinuity is due to the local geometry of the surface. So near to the poles, if there is a terrace, this is a particular pole, correct? If you look in this direction, you will induce concentric circles, and these terraces will act as a change in the local geometry. So there will be there is a change in the electric field, there will be a discontinuity in the electric field. So the distribution of the electrostatic field around these zones tend to divert the ion trajectories. Okay, as these zones, these terraces or the zones are actually have a high density of electric field distribution. Okay, so if you have a high high density of electric field distribution, then locally the atoms which are located in these regions, they get ionized, and due to the curvature effect, these ionized atoms, these atoms gets repelled each other, due to which they divert the ion trajectories. Okay, so in the last class I have given you in the few 2 or 3 classes before, I have given you an example where if there is a change in curvature on the tip surface, usually in FDM these atoms when get ionized, that flight path will not be at a straight path, will not be along the field lines. This flight path will be diverted. The ion trajectories are diverted. So you will see on the detector low density regions just ahead of that particular high radius of curvature region. So you will have a low density, low atomic density, and here high atomic density. Okay. So these are called trajectory aberrations, and these diversion of these ion trajectories, okay, these artifacts are directly related to the crystal structure. Okay, and also the condition of experiment, or we can say that temperature and the electric field. Okay, so the diversion of ion trajectories is related to the crystal structure and also the experimental conditions, which is related to your temperature and the distribution of electric field. Okay, it means that the shape is controlled by these factors during field evaporation. Okay, so usually these depleted zones regions are called zone lines or poles, low density regions. Okay, so this is related to your trajectory aberrations. This is as I told you, these trajectory aberrations are of two kinds. So one is intrinsically related to the atom probe tip, okay, and the electric field distribution in the vicinity of that. There is another way of trajectory aberrations is from precipitates. Okay, so if you are in your matrix, if you have a needle specimen, if your matrix there is a precipitate at the apex of the needle specimen, if the field evaporation or the evaporation field of this precipitate is different from the matrix, then this also can arise to the trajectory aberrations. This depends upon the difference. This depends on the relative difference between the evaporation field of the precipitate and the evaporation field of the matrix. So there will be two conditions, correct? So if when the field requires to field evaporate the precipitate the matrix, so when the electric field which is required to field evaporate a precipitate is lower or higher than the matrix. Okay, so the relative difference will arises with the difference in evaporation field required to field evaporate a precipitate. Either it is lower than the matrix or either it is a higher than the matrix. If it is lower than the matrix, this is referred to as low field precipitate, and if it is higher than the matrix, the evaporation field of the precipitate higher than the matrix, these are called high field precipitate. Okay, so this low field precipitate, usually what will happen if you have a needle specimen, okay, and if you have a detector here, if you have a precipitate, if this precipitate has low field or low evaporation field than the matrix, then what will happen is usually this curvature which gets flattens. Due to this flattening, the atoms from the matrix, it gets deflected inwards. Okay, so this causes a flattening of the surface of the needle specimen. Okay, so if you zoom out, you will have a precipitate which is get flattened on the needle specimen, and the atoms near to the surface will get deflected inwards. in the case of low field precipitates. So this results in a lower field regions that deflects the ion trajectories inwards. So it results in a lower field regions that deflects the ion trajectories inwards. It means that at this location in front of this precipitate there will be a high density of atoms or ions, and here there will be a low density. This is due to the flattening of the surface because of the low field precipitate present in the matrix. It means that if the precipitate evaporation field, the evaporation field required for the precipitate is lower than the matrix, usually the precipitates will field evaporate very easily. So the surface, the evaporation surface, the surface gets flattened, due to which the atoms in the matrix will get deflected inwards, and you will get a very high density of ions just above that field precipitates. Okay. In the case of high field precipitates, you have a needle specimen, you have a precipitate, this is having a high field, means evaporation field required for the precipitate is more than the matrix. Then what will happen, if there is a detector here, what will happen is this particular precipitate, it gets bulged out. Okay. It means that the radius of curvature increases. The radius of curvature increases. It means that the electrostatic field distribution in the needle specimen, if you magnify this, then you will have a tip, you have a precipitate like this. Okay, and if you have a detector, this particular region we have a high electric field distribution. Okay, and due to this high electric distribution, what will happen is the atoms which are get ionized, they will reflect themselves. The ions will reflect themselves, and these ions will be deflected away from the region. So in the detector you will see a low density of atoms or the ions on the detector, and you will see a high density away from that precipitate location. Okay, so this is the difference between the low field precipitate and high field precipitate, and these condition also can be regarded as a trajectory aberration. Okay, so locally it generates a very high field. Locally it generates a high field because the precipitate needs higher field evaporation. So by the time the atoms get ionized from the matrix, it gets sharper and sharper. And due to this local change in the curvature, the electric field distribution become intense or the denser, and due to which the atoms which get ionized in the matrix will be reflected. And due to that reflection, usually the trajectories will get deflected away from the surface or the sharp surface or the precipitate. Okay, and this results in a decrease in the density of atoms which are hitting just ahead of the precipitate. Okay, so this is a second type of aberration which is called as a trajectory aberration. So first was the roll up, the second one is the trajectory aberrations, and the third type of aberration is related to a so if you are in a needle specimen, there are certain atoms which needs high evaporation field for field evaporation. If these atoms or the species needs high evaporation field for the field evaporation, then what will happen is then even though you are applying an electric field, as this requires higher field, these atoms are retained on the surface, until it finally gets enough enough electric field, intense electric field, or the evaporation field evaporation, such that these atoms can field evaporate. So the atom stays longer time at the surface. Okay, and this longer time stay at the surface, this is called preferential retention. Preferential retention. Okay, and this preferential retention causes error in the atom location in the reconstruction, due to which there will be a error in the composition profiles, especially in the location where the grain boundaries are present. Correct? So this is the preferential retention of atom. If the atoms present in the needle specimen have a low evaporation field, then it will have a opposite effect. Okay, so the field evaporation before the most, so if in the needle specimen, if there are protruding atoms, which needs to be field evaporated, but there are also atoms which is having a low evaporation field. What will happen, that if there is a low evaporation field, even though these protruding atoms did not field evaporated, these low evaporation field atoms or the species gets field evaporated before these protruding atoms. Okay, and this directly related to your chemical nature. It means that it is directly related to the strength of bonds between those atomic species, between the nearest neighbors. Okay, and this particular aberration, which we also call as a chromatic aberration. Okay, this is particularly the chromatic aberration. Okay, so we discussed mainly three types of aberrations, which is rollover or roll up, trajectory aberrations, which can be due to the intrinsically the specimen, the type of specimen and the electric field distribution, and the other is the if there is a precipitate which is having a different evaporation field values than the matrix, and another is the species which is having a different species or atoms which are having a different evaporation field values than the matrix. It usually called the preferential retention. Okay, preferential retention, when the field evaporation of those solutes or the species are more than the matrix. Correct? This particular effect usually affects the depth resolution of ions. Okay, remember, as I told you, the z coordinate is a sequential process. Okay, and this sequence of process is layer by layer, and this sequential process, it depends upon the penetration of electric field on the surface. This penetration of electric field on the surface is less than the interplanar spacing of that particular atomic layer. Okay, so this is a sequential process. Now this aberration these aberrations, chromatic aberrations or trajectory aberrations, this directly affects the depth resolution of the ion. Okay, so usually as I told you, the reconstruction, during reconstruction it is built by layer. Okay, and if there is a difference in the evaporation field of solutes and the matrix, or the precipitate and the matrix, so what will happen is the low evaporation field species will depart the needle specimen very early. Okay, so it means that the reconstruction, if it departs early, then it will be detected very early than the other atoms or the ions from the matrix. So in the reconstruction, this will be reconstructed early. Okay, so it will directly impact on the accuracy of the atomic position along the z direction. The depth, z direction means in the depth direction. Fine. Okay, so this is how it affects the depth resolution of this particular aberration, chromatic aberration or the trajectory aberrations will affect the z coordinate. Okay, there is another issue which is called surface migration. Okay, we will discuss about the surface migration. This is another type of artifact usually we will get in the tomographic reconstruction. Okay, so in the image we know that the zones or the poles display high concentration of solutes in the vicinity of poles and zone lines. This surface migration causes the regions or the zones that display a high concentration of solutes in the poles and the zone regions. Okay, this is due to because these poles and zones are the regions of high field gradients. Okay, so along with the trajectory aberrations, even surface migration can take place. For example, in an aluminum copper magnesium alloy, it can happen that preferentially there will be a loss of aluminum atoms at the region of poles, which leads to the higher concentration of copper and magnesium at the poles. Okay, and the loss of aluminum atoms is related to your trajectory aberrations. Okay, so this might lead to the composition which can be seen as a higher concentration at the poles. Okay, and the copper and magnesium atoms which are present in that, these are actually less affected by the trajectory aberrations. Okay, so this is related to your surface migration. So usually the high concentration of solutes, usually they are seen in the poles and zones. Okay, it means that these are related to the crystallographic features. Okay, and in steels we see that some of the solutes get surface migrated to these poles. Okay, and this is related to your surface migration. Okay, so similarly in film we see this surface migration in film. So this is due to the under a very strong field gradients at the surface of the specimen. This leads to the atoms can relocate from one position to an adjacent one by a, usually it is a thermally assisted process. Okay, and due to the field gradients near to these poles, it induces the difference in relative energies between the atomic sites. That these two regions facilitates the diffusion process. This is related to the surface migration. Okay, so if the solutes have high evaporation field, means higher than the matrix, these are preferentially retained, as I told you before. These are preferentially retained. So they are spending more time on the surface. It means that they are more prone to surface migration process. Okay, remember this is different from trajectory aberrations, or which are related to your field distribution, the intensity of field distribution on near to the poles or the ions. Okay, and this surface migration is a thermally assisted process. Okay, and this thermally assisted process, these surface migrations, actually you can minimize by lowering the temperature, much below the 50 Kelvin or near to the 20 Kelvin. But even though if it goes to the lower temperature, we cannot, due to the difference in the evaporation fields, your trajectory aberrations you cannot avoid. Okay, so these are the two important things, surface migration and trajectory aberrations, which are little bit different. Surface migration is a thermally activated process, and it usually the solutes, if the solutes gets field evaporated much earlier near to the poles or zones, then you will get a higher concentration of copper. And example, if you have the matrix atom, if the matrix atoms field evaporates at these zones much earlier, then you will get higher amount of solutes at these zones. Okay, and also due to this field gradients, and you can actually this assist the diffusion process. So usually the solutes which is having a higher electric field, which are retained and which are stays on the surface for longer time, can actually diffuse along these zone lines or the poles. And usually it is a thermally assisted process, and the thermally assisted process, it can be minimized by lowering the temperature. However, even though if lower temperatures, due to the trajectory aberrations, there will be some inconsistency in the reconstructions. Okay, so we discussed about in this class that there are different types of artifacts which are related to the first artifact which we does is a rollover, which usually happens near to the atomic terraces. The second is trajectory aberrations, and this can be intrinsically related to the needle specimen and the distribution of field in the vicinity of the atom probe tip, and also if there is a difference in the evaporation field of precipitates and the matrix. So you will get a different regions of atomic density on the detectors, depending upon whether the precipitate evaporation field is low or higher than the matrix. The third one we discussed is if there is a difference in the evaporation field of atoms or species from the matrix, it might create a retention of that atomic species, or it might be early departure of those species. Okay, and the fourth thing we called it as a surface migration. which also occurs near to the poles or the zone lines, okay, due to the, and this is a thermally activated process which can be minimized or which can be removed when the temperature goes low temperatures. However, at low temperatures you cannot avoid these trajectory aberrations. Fine. So with this I will end this class now, and I hope you must have got an idea that how the trajectory, how these artifacts can come up, which are, some of them are experimentally produced, and some of them are the reconstruction. So during reconstruction, what will be the artifact, that we will discuss in the later classes, but experimentally these are the aberrations which we usually see due to the local electric field distribution that creates the deflection of field lines, due to which the solutes or the matrix atoms gets deflected and creates a low density regions and high density regions. So with this I will end this class, and we'll meet on the next class. Thank you.